This talk is about scrambling and descrambling the supra-atom multiverse. It's basically talks about quantum fields in the universe through space-time, and about some multiverse pictures, and also about quantum entanglement in space-time. C.Jayant Praharaj band photonics materials. This slide is basically give a picture of something we work on. So there are different energy scales and length scales in the universe, and this is basically showing a semiconductor expert works on. For example, these are indium gallium nitride alloys, and these are band gaps and lattice constants, and you have the fact that non-relativistic and relativistic entanglement generation can be done through structured design and device design in these pictures. So we have, and it can be part of a supra-atom time evolution. The next slide basically shows QCD as an example interaction regimes, quantum chromodynamics, and we basically have up quarks, down quarks, and strange quarks. So you have the SU3 group, which controls the behavior of the quarks. So you have SU3 flavor quarks, and they have coupling to non-abelian gauge SU3 color gluons. And actually, there are 6 flavors of quarks. So, and further, the quarks themselves have colors. So it's actually 6 times 3, which is 18 kinds of quarks. And the picture below shows a typical interaction between up and down quark by the exchange of gluons. And the gluons come in different colors, and basically there are 8 different gluons in the representation, which is relevant for various QCD phenomena, for example, that are seen in nuclei where neutrons and protons interact. You have a strong force, and the basic interaction is due to this gluon exchange between up and down quarks, and which manifests itself and then as internuclear interaction. This is part of a supra-atom universe time evolution. There's an entanglement structure which is determined by measurement sequences, and this can lead to a scramble configuration. And it should also mention here that as can we'll see in later slides how this kind of interaction can become relevant. Now, this is just an example of the interaction regimes that are seen in the quantum world, in the universe. And you have, of course, other kinds of forces and interactions. For example, you have the electroweak interactions, and there are W and Z gauge bosons and all. And there are potentially other interactions that are unknown that could be discovered down the line. And we'll come back to this later as well, when we try to understand what kind of entanglement regimes can be expected in the supra-atom universe and supra-atom multiverse pictures. You can have energy pumps, which basically focus a lot of energy into a small space region, and this can lead to ultraviolet probes, and highly localized evaluation of quantum operator values can lead to some large changes in metric. And the The idea is that operator value determination along with restriction of measurements to specific part of phase space leads to scrambling. Here we have a picture of space-time manifolds with entanglement across multiple. Before showing this, we try to get into some more details about the kinds of fields that are involved in a multiverse picture, for example. This slide basically talks about some basic Lagrangians and Hamiltonians and things like that of fundamental fields in nature that scientists have been studying, physicists have been studying for several decades. For example, there is a Lagrangian here, which is basically a modification of the Klein-Gordon Lagrangian. And it basically shows a field, which is a scalar field with a mass. And you can set about trying to find the equations of motion for this field. And you can also go about finding canonical momenta and canonical coordinates, and then you can impose commutation relations, quantum mechanical commutation relations on these. You can expand these fields, which you can see these fields have values at each region of space-time. You can expand them in Fourier components, and then you can quantize this field, and you can get a Hamiltonian, and you can see that this Hamiltonian looks very much like a multi-mode harmonic oscillator Hamiltonian with some 0-point energy factor that is sitting there. So this is an example of a typical field one can encounter, but there are other kinds of fields and of higher and higher complexities, and we need to consider those when understanding the kinds of quantum states and the kinds of entanglement that you can get in a space-time kind of picture. And here we have some further examples of quantum fields. So the previous field could be a matter field, for example, matter, and then we have what's called, if you broadly try to distinguish between matter and energy from a classical perspective and try to take it to the quantum world, then you have fields that quantize for energy-like phenomena, and these turn out to be force carriers. For example, here shown is the Maxwell Lagrangian, which has this vector potential and then this field tensor. This can be quantized, and this quantization basically leads to photons, which is again another kind of harmonic oscillator quantization. Not all quantizations look like harmonic oscillator quantizations, but yeah, you can have other kinds of quantization. For example, we'll see the Dirac field for leptons, the primary example being electrons, which looks slightly different. But quantizing this Maxwell Lagrangian leads to a Hamiltonian, which basically has photons. So these are basically the quanta of the electromagnetic field. Now there are further modifications. In this picture, we don't have magnetic monopoles. We can have magnetic dipoles, fundamental magnetic dipoles, like spin of the electron and its intrinsic magnetic moment. But you can have more advanced theories which incorporate magnetic monopoles. And in many theories, the magnetic monopole leads to charge quantization. So that is aspect. So we are just looking at some of the details of these fields involved in order to understand the entanglement picture. So this slide discusses the four component spinners basically, and then some special space and time derivatives, and then there is a mass. And when the mass is zero, this can basically split into two what are called the left-handed and right-handed Weyl fermions, and these are called Weyl equations. You can go upset about quantizing this, and when you do, you end up with this Hamiltonian, and this Hamiltonian has an interesting aspect when you try to take care of energy conservation and causality and all such details which you want in a sensible quantum picture. You end up with a Hamiltonian which basically has these excitations with some dispersion, and these are electronic excitations, electron excitations. Then you have the positron or the antimatter excitations as well. So this field has both matter and antimatter in it, and you can see that several. So these are aspects which are specific to the field you are looking at, that you can have matter and antimatter excitations in certain kinds of fields. And you can see that you can have this spinor field which has been Fourier decomposed. And after Fourier decomposing, you quantize it and you end up with this Hamiltonian shown below, and where you have matter and antimatter. And then you can have multiple fields and you can have coupling between them. This slide shows basically QED Lagrangian with multiple fields and then coupling between them through what is called a covariant derivative. And these are all relevant when we consider the kinds of the kinds of states and entanglements that we can get. We consider some details about the physical state of understanding we have about these theories. And you can see, for example, in these theories with multiple fields and coupling, you can have interactions or scattering between particles. For example, an electron can emit photons, and an electron can also absorb a photon. And so you can have interaction between two electrons mediated by that. And furthermore, you can have more complicated pictures where the photon can give an electron and a positron, a matter antimatter, and they can later annihilate to again give back a photon. So all these are interaction pictures that arise in these coupled Hamiltonians. And what happens is that if you try to calculate some scattering amplitudes in these quantum field theories, you get some infinities in these space pictures. And then you have to do what is called renormalization. For example, while calculating scattering, you can get infinite amplitudes, and what you can do is if you take what is called, for example, the bare charge of the electron, and it gets multiplied by an infinite factor, and if you define that as the physical charge of the electron, then you have basically renormalized. You have basically got rid of the infinity, and you have basically renormalized it to get finite numbers. So you can do that. There is similar renormalization for the mass, where you can basically renormalize the bare mass and get the physical mass after getting rid of the infinite terms. So these are all these multiplication term factors involving infinities. These Z1s and Z2s and Z3s are all factors involving infinities. And you have charges and masses and amplitude and vertex quantities that you can renormalize. And you take from the bare quantities, you basically get to the renormalized quantities, and that's how you get rid of infinities. Once you do that, you then get finite answers, and then you can calculate certain quantities to great degrees of precision, and you can then compare with experiment, and in fact, the experiments agree in great detail with the theories. So that is the reason for going through this renormalization procedure. And this is one. Then you have what are called granular unified theories, which try to incorporate symmetric groups to unify all the different forces under one symmetric group. And you have this representation of these, for example, these different quarks and leptons as reducible SU5 representation of 5 bar plus 10 representation. And in this picture, you can have some interesting phenomena that are not there in the standard model. The standard model is typically basically some of the slides we discussed previously, but you can go beyond the standard model and there can be other phenomena. And people are looking for some of these phenomena that have been predicted based on that to say if this extended grand unified theory pictures are right or not. And along the way, you have these running of coupling constants, or what is called renormalization of coupling constants. And then you have, for example, you have electroweak forces and strong forces, and they have different coupling constants of different coupling magnitudes at given energy scale. But if you try to extrapolate them to high enough energy, then there is an energy around which the predictions is that they become the same, the coupling constants become the same. And the three couplings tend to join around 10 to the power 15 GeV into a single coupling alpha GUT. Yeah, then I again go back to some of the Gauss theories to look in greater detail at. For example, we looked at the Maxwell field, and that had the quantization as photons. But if you have the weak interaction and the strong interaction, you have the force carriers are basically the force carriers are basically some higher higher Gauss fields that come in, and they're basically non-abelian. Yeah, there's a non-abelian Gauss invariance that is involved in defining these fields. And so in general, a coupled field for, let's say, Dirac kind of fermions with these generalized fields looks like this. You have the covariant derivative term, and then the field tensor term, and then some possible topological terms, and then the mass dependent terms. And you have this structure of this commutator between the covariant derivative given in terms of the field tensor and some matrices, which basically are related to the SU2 or SU3 groups, and that gives rise to the name Gauss field, non-abelian Gauss theories for these fields. And for example, for the strong interaction, you basically have 8 gluons, which are representations of the SU3 group, which carry the strong interaction as we showed schematically in a previous slide. So this is the mathematics that on which that schematic is based. And so this basically shows the Lagrangian that is involved, and you can then quantize these and you get gluons. And then the only difference is gluons are different from photons. Photons don't interact with photons. Photons interact with leptons and quarks, but not with them each other fundamentally. But the gluons are interacting. So the gluons interact. They both carry charges between quarks in the strong interaction, but they also interact with each other. So that gives rise to more sophisticated phenomena in the quantum chromodynamics QCD picture. Then you have what is called a Higgs field, and so the Higgs field is basically a complex this term with a potential function which is given by this, and then this potential can have what is called spontaneous symmetry breaking, and the phi, that field value that is shown here, can take on a specific expectation value, and when you do that, when you expand around the new field value of phi, you basically get a modified Lagrangian which has a mass term for the photon. For example, if it's coupled to a photon, this gives a photon mass term, and if it is also example, this can give rise to the masses for the W bosons and Z bosons that weak interaction potential with top quark. This also has some cosmological implications that you can have in the Big Bang picture, the very early stages of the universe. You can have what is called you can have a rapid inflation due to then that in that the Higgs field is involved. This is just some more details along the same lines with some schematics. And so you have supergroups controls interactions. You have quark sector shown here with isospin. You have leptons with spin. And the supra-atom universe time evolution delineated entanglement structure is determined. The same is true if you have multiverse pictures. For example, in a multiverse picture like this, you can have space-time manifolds, and you can have, for example, there's the different kinds of multiverse pictures, and we'll try to discuss some of those next. There is something called the cosmological constant problem, where the 0-point energies of the various quantum fields that we discussed can potentially give rise to some curvature of space-time, and this needs to be fine-tuned, and therefore theories need to get the right cosmological constant in agreement with experiment. This slide shows a brain war picture. This is in the string theory picture. You have what are called these open loop strings, which end on which can end on on, on, on these so-called brains, which are these rectangular things shown here. And then you have the closed loop strings, closed strings, which can basically detach from the brains and flora. And that gives rise to, and you can have different length scales, time scales involved. Go into details of the quantitatives in this slide, but you can basically then get into the different multiverse pictures where you basically have these multiverses living on these different brain worlds. So we are living on strings which are associated with one kind of brain world, and then you can have different kinds of brain world. This is just the same brain world picture. This slide basically moves on to string theory and shows the schematics of string interactions, and the fact that these string interactions you see has this dimensionality that where the previous interactions we showed in some of the previous slides for quantum field theories, which showed these lines as the propagating particles, and then the force carrying photons, gluons, etc. Here there is, you can, due to the dimensionality, the fact that strings are one-dimensional objects, so their interactions has this dimensionality associated with it, and that gets rid of many of the infinities associated in the renormalization theories and makes these all renormalizable. And that is very important for renormalizing gravity, these pictures. We next move to what is called CY manifolds, Calabi Y manifolds associated with the string theories. So string theories in string come with extra dimensions. So the basic idea is that they get rid of the infinities involved in quantizing gravity, for example. But for example, the superstrings live in 10 or 11 dimensions. So the thing is, our ordinary world seems to be made of 3 space and 1 time dimensions. So there are these extra dimensions of, there are these extra spatial dimensions in string theory. So the question of why they aren't observed basically is answered by the fact, the technical term is what is called compactification, which means they are basically curled up. And you need to go to very high energies in order to observe them. So at ordinary energies, which are even at the high energies available at, for example, the Large Hadron Collider, it's difficult to see to see string phenomena, although that might change in the future as the energy at the Large Hadron Collider is increased. But for now, at least, we don't have access to the kind of energy scales required to access these extra dimensions. And in this compactification picture, what it calls Calabi Y manifolds or Calabi Y shapes that emerge mathematically when we try to compactify and to explain why these extra dimensions aren't visible to ordinary experiments. And these basically show some of the parametrizations of some of the Calabi Y manifolds. And the basic idea is that there are numerous kinds of Calabi Y manifolds that are potentially there. And then you can move on to more sophisticated ideas like compactification and toroidal orbifolds. Certain topological entities, and you then do compactification on these toroidal orbifolds, and then you basically try to get rid of some of the plethora of shapes of Calabi Y manifold shapes that you get when you try to compactify the extra dimensions in string theory. So these are basically some way of compactification and to get sensible answers that you can compare with experiments instead of having to deal with so many numerous possible ways of compactifying that you need to sort through the experiment and then compare with experiments becomes a difficult task. So these are some more advanced ideas about compactification. And then you have M theory, which basically leads to n dimensions instead of 10 and some dualities in string theories. And the next is inflationary cosmology, and these basically are some of the, for example, uh, the length scale parameters of the universe involved and how the rate of change of these through time. When we, for example, add the influence of the Higgs field. So you have the ordinary Big Bang cosmology, and then when you add the effect of the in Higgs field, you get to inflationary cosmology and a large uh, part uh, rate of expansion in the very early stages of the universe, and that can be understood in terms of the Higgs field and inflationary cosmology. So next we come to black holes and quantum systems. We're basically shown two black holes just schematically, and this is the classical Schwarzschild description of the black hole with the Schwarzschild radius. Ways to try to do quantum mechanics on these black hole fields and basically have what is called the entropy of the Bekenstein-Hawking entropy of the black hole, which is given by the area over 4gh, where g is the gravitational constant, a is the area of the black hole given by the Schwarzschild radius, and h is Planck's constant. There are recent ideas which basically try to understand this entropy in terms of states living on the horizon, and in, in terms of holography, for example. Basic idea is that the black holes can entropy is kind of a measure of uh, entropy is a measure of disorder in the classical thermodynamical view. They then have the question of what happens when you have matter fall into black holes and what happens to entangled quantum states and to the information that is contained uh, in these black holes. In the matter that falls into these black holes, and that is actually a lot of progress has been made in understanding those, uh, uh, but there are still some mysteries that remain about what happens to the information. And so when you consider large time scales and length scales of the universe, the same kind of paradoxes and questions continue. So we don't fully understand what happens to information on these kind of scales when this kind of extreme environments are involved. Now, we don't, since we are talking about multiverses in this picture and the supra-atom multiverse, we'll just mention this briefly. But the basic idea is that there is a question about what happens to information when black holes are involved and when extreme environments like the uh, like space-time regions close to the be, beginning of the close to uh, uh, the supposed beginning of the Big Bang are involved. This slide basically shows all the quantum field theories that we talked about. try to understand it in perspective with the with an expanding universe picture, which was stemmed from Hubble's observation about the fact that galaxies are moving away from one another. And you try to understand, then there is the hot Big Bang picture, and from that, Gamow was able to predict a microwave background, and that was discovered several decades ago. But then the inflationary picture came in to explain some of the paradoxical features about this hot Big Bang theory. And that has these fluctuations of this microwave background radiation. So there are the anisotropies, and then there are these multiple fluctuations of the cosmic microwave background that matches the theory very well. And these are some of the anisotropies that people are still trying to understand. And next, just move on to some representations of black holes and white holes. And so, for example, because these kind of form a natural gateway for the multiverse picture, because if you can have black holes and then you can have white holes, from black holes, classically, nothing can escape. Quantum mechanically, there is Hawking radiation from black holes. But classically, from a black hole, nothing can escape. Quantum mechanically, some can. And then if you can move on to white holes, from which everything which holds everything escapes. So you can have pictures where you have black holes connected to white holes, and then this takes us to neighboring universes and things like that. So there are different kinds of metrics that are used, named after the scientists who frame those metrics. So you have the Kruskal-Szekeres metric, and they have Penrose metric, and then you have they have defined these coordinates, which are basically transformations of the Schwarzschild coordinates that we showed in the previous slides. And the Penrose uses coordinates which are based on the Kruskal-Szekeres metric, and using this, Penrose can basically draw diagrams for the horizons and singularities and things like that of black holes and white holes. You can have universes and parallel, so these are so-called Penrose diagrams. You can have universes and parallel universes, and you have these horizons and anti-horizons. You have black holes and white holes, and then you have wormholes connect. So this is, on the right is a schematic picture of a wormhole connecting these. So the basic the thing is the example. Let's go back to a previous slide. So this is one way you can get to white holes or wormholes. It's a kind of a not very quantum. This is more of a classical general relativistic picture. But if you go back to, for example, these strings and Calabi-Wide manifolds that we discussed previously, each of these ways of compactifying the extra dimensions can potentially give rise to a universe, and so you can have multiverses based on these Calabi-Wide manifolds. So this conjecture, but it's not inconceivable that you can have multiverses. The question is, can you have, for example, quantum between multiverses that go beyond whatever theory has been considered in arriving at these in the string frameworks. But that is the topic, one of the motivations for the topic of the talk about can we then in a supra-atom multiverse where the single atom looks, the single universe, one universe looks like a superatom, but you have supra-atom multiverse, and then you have measurements in time, and we can scramble them. But does this scrambling or information scrambling or quantum measurements, can it happen over multiverses? Can it affect multiverses simultaneously? So these are questions that need to be addressed in the multiverse picture if we want to understand the quantum multiverse picture in greater detail. So this is one multiverse picture, but this is more of a general relativistic, not classical kind of picture, and this is more of a quantum picture using strings, which are used for to quantize gravity, especially along with all the other forces are known in nature. These are some just typical relativistic landscapes because they lead to multiverse pictures. So in conclusion, we have the de-Sitter space quantum field interactions determine the course of time evolution. The operator value determination can lead to large metric changes in scrambling, and multiverse descrambling can be the result of operator value determination. So here the thing is, as I said, in the Calabi manifold picture, you can have scrambling taking place between multiverses, but you can have descrambling. And if we go back to this picture, so you can then use energy pumps to ultraviolet probes, and then need to design basically ways of again regenerating entanglement, descrambling over large uh, scales and potentially time scales. Could be combination of combination of large scales with different kinds, space scales with different kinds of time scales, and then over multiverses. So that is the fact that you can scramble and then potentially descramble. And what are the limits? What are the limits up to which you can? Multiverse descrambling can be the result of operator value sequences that lead to phase-specific consolidation. Scrambled configurations can result due to measurement sequences. Basically, about the scrambling of the supra-atom multiverse thing.